Okay, so let's take a look at these couple of examples that involve definite integrals now. And as I mentioned here in the notes, I say you can approach these definite integrals in a similar way to what we were just doing with the indefinite integrals. And after you get your antiderivative, you can plug in your upper limit, subtract what you get when you plug in your lower limit. But there's an easier way to handle it, and you'll see exactly what I'm talking about here. So I'm going to rewrite the entire definite integral in terms of u. So that means I'm going to rewrite the integrand in terms of u, but I'm also going to be rewriting the limits in terms of u. And so I'm going to be creating an entirely new problem. And when we have that entirely new problem, it's going to be an easy process from there. You'll see exactly what I mean. So I see a composite function. I'm going to let u equal x cubed plus 8. That's the inner part of the composite function. My du in this case would be 3x squared dx. Do you have 3x squared dx in the integrand? No, you don't. So if you wanted, you know what, I should just do this. I should write the 3 in front of the x squared. So that way you could see, now we have 3x squared dx, but then I also have to offset that with the 1/3 in front. But when I rewrite this, I'm going to say 1/3 integral of u squared times du. That's my u squared. 3x squared dx is my du. But it would be wrong if I wrote -2 and 4 right here, because if all of this is in terms of u, it's actually appropriate to write these limits of integration to be in terms of u also. And so I'm putting boxes here because we're going to fill those boxes in. When x is equal to -2, we can plug -2 into this ux relationship. And if we plug -2 in for x, we're going to get -2 times -2 times -2. That's -8 plus 8. U is equal to 0 right there. And then when x is equal to 4, we'd have 4 cubed. So that's 64 plus 8. So that's going to be 72. But here's the cool thing. This is an entirely new problem at this point. If my integrand is in terms of u and my limits of integration are in terms of u, then that means no back substituting or anything has to be done as we proceed. So I can just finish this question out by saying, okay, this is u cubed over 3, and I'm going to evaluate u from 72 down to 0. So we end up with 72 cubed divided by 9. And 72 cubed divided by 9 is a good answer. And the nice way to check this type of problem is go back into what we did, what you saw before, how we could do this in the calculator. You know, you could, into the y equals menu, you could put in x squared times x cubed plus 8 quantity squared, and then go into second calc, or no, it was second, I believe it was second trace, and that took you into the calc menu. And once you're inside that calc menu, I think it was number 7 was that integral symbol, and then you could put in the lower limit, the upper limit. It would shade the region, and it should give you the exact same value that we're getting here. So that's the best way to check those. Make sure that you can do some of these by hand, and you're not always relying on just the calculator to do it, because it will find a way to hurt you a little bit in Calc 2 if you're simply always doing it in the calculator. You need to know the algebraic strategies that you can use for doing integration. All right, number 10, same type of problem. You see a composite function because it's e to this big old mess right here. So I'm going to let u equal that mess. I'm going to let u equal this -x squared over 2. So that means du would be equal to the derivative of this. That's going to be -2x over 2. So that's just -x dx. Do you have a -x dx in the problem? No, but you do have an x dx. So if you put a negative there, then I'm going to put a negative out front also. But when I rewrite this, since I have limits of integration, I'm going to change the limits of integration to be in terms of u also. And so I've got, in the integrand, I've got e to the u, and then, I needed to have that in there. There we go. We had the -x dx was my du. So I have e to the u du in the integrand. And then these limits of integration are going to get changed. So when x was equal to 0, so I'm going into this ux equation. When x was equal to 0, u would be equal to 0 also. Okay? And then when x is equal to the square root of 2, the square root of 2 squared is 2. Negative 2 divided by 2 is negative 1. And so your upper limit actually becomes negative 1. Now, you can continue from this point, and this is a completely new problem like we just saw in the previous example. But most of the time, isn't our upper limit the larger number? And in this case, negative 1 is the smaller number between 0 and negative 1. So one option that you do have is you can apply, this would be a perfect place to apply a certain property of integrals that says we can flip the limits of integration. And when you flip the limits of integration, then you negate the sign, you change the sign of your definite integral. And so right now, if it's negative definite integral from 0 to negative 1, that's the exact same thing as positive definite integral from negative 1 to 0 of e to the u du. And again, this is our entirely new problem. We don't have to do any back substituting. The antiderivative of e to the u is e to the u. I'm going to plug in my upper limit, subtract what I get when I plug in my lower. So we're going to end up with e to the 0, so that's 1, minus e to the negative 1. So your final answer, 1 minus e to the negative 1. Again, check that in your calculator, put it into the y equals menu, look at the graph, go to number 7 in that second trace calc menu, and you'll see the shaded region is going to be the exact same as the value 1 minus e to the negative 1. Okay, so this is the process that I love to do when I'm evaluating a definite integral using integration by substitution. But like I said at the very beginning of this video, you've got another option. You can approach this by doing exactly what we were doing before, where we simply found antiderivatives, eventually get, where you would eventually get your function or your antiderivative in terms of x, and then you can use your original limits of integration. But you could see here, when you change everything to be in terms of u, including the limits of integration, and you create that entirely new problem from that certain point, the question is actually pretty easily answered. So I suggest this strategy. Okay, so check out the next video for some exit problems, some practice problems.